Okay, so good morning everyone. My name is Akshitha and I'm the sales specialist for high power rectifiers working with ABB. And today's session is going to be powering gigawatt size green hydrogen facilities. So for the past few days we've been hearing a lot about scaling up of the electrolyzers, but nobody's talking about scaling up on the power supply side. So we have a lot of advantages on scaling up on the power supply side. So that's what we look at today. So yeah, these are contributors for the presentation. Agenda, we look at an overview SLD for a large-scale hydrogen plant, the challenges and advantages we have, the overall electrification solutions, and then the conclusion. So here we have these two SLDs. So on the left-hand side, we have a block which is 120 megawatts. That's our base block, which we'd like to call. And this is primarily dictated by the availability of the MV switchgear available. So we have the 120 megawatt block based on 5 megawatt electrolyzers, and on the other side we have the 20 megawatt electrolyzer. And visually itself, we can see there's such a difference in the number of components which we have when going in with the 5 megawatt and how it decreases with the 20 megawatt or the bigger electrolyzers. And to explain the setup, so we have each electrolyzer is connected to one rectifier, and then two of the rectifiers, which are 6 pulse, each are packaged together, and then they are connected to one 12 pulse transformer. And then from the transformer upwards, we have the MV switchgear, and then to maintain a common, for the sake of comparison, the HV switchgear is the same. So going into the comparison of this head to head, so we take the 120 megawatt block, and 8 such blocks form a 960 megawatt, which is just shy of 1 gigawatt. So on the HV side, we have the plant capacity of 960 megawatts. So we have the 8 bus bars. So there's going to be 8 HV switchgears, which are common on both the sides. Now coming to the differences. So with a 5 megawatt electrolyzer setup, we have to deal with 96 MV switchgears and DC power supplies. But on the 20 megawatt side, that just drops down to 24. So that gives a lot of advantages when we are scaling up. And coming to the rectifier and the transformer, yes, we are dealing with a bigger transformer, and we are dealing with higher currents on the rectifiers, but we are dealing with much smaller number of quantities. And harmonic filter, so this is a big topic which everyone's talking about, the power quality and the efficiency. So when we say harmonic filters in the 5 megawatt size, depending on the type of rectifier chosen, so if it's IGBT or we have the IGBT, we have the diode based with the IGBT chopper, or we have a thyristor rectifier. So depending on that topology, we will need filters and we will need dynamic compensation. On the 20 megawatt electrolyzer, we would have to go with the thyristor technology, and in that case, we need the filters connected to the MV bus. And talking about the dynamic compensation, this is only a big factor, or it comes into play because of the fluctuations on the grid. It's not, okay, thyristor needs this power quality, thyristor is less efficient. I would not say that, but it's contributed. Why? Because of the large range of operating scenarios which the electrolyzers are going to be operating at because of the fluctuations on the grid. So if we have a strong grid, if we have a hydro grid, if we have a nuclear grid, something very stable, the filter issue is not going to be big. So all the chemical plants out there using thyristor rectifiers, we have standard static filters, and we've delivered multiple such projects around the world, and yeah, it's a market standard. So further comparing, typically the core product which we are offering is the rectifier and the transformer package. So like we discussed in the previous slide, so when I'm doing with the 20 megawatt electrolyzers, I have 24 units. And with the 5 megawatt electrolyzers, it's 96. So there is a 75% reduction in the number of components right there. And the reduction in the components means lesser areas, lesser number of problems when dealing with the logistics, the project's execution becomes easier. And going to the footprint requirements. So there's at least a 50% requirement when I'm going with a larger electrolyzer. And then weight. Yes, each transformer, each rectifier in the bigger setup is going to weigh more, is going to be slightly larger. But on the overall, I'm going to still have an 18% reduction in the weight which I have to deal with, which it makes it easier on the civil side, on the construction side, which is a very expensive affair when it comes to the EPCs. So, and on the losses also, for the rectifier and transformer, we see there is a 17% reduction in the losses in the core transformer and the rectifier block. And coming to cost, everyone is very keen on the cost, and it's an important decision-making factor here. So in the 20 megawatt electrolyzers, or as we are going larger scale, even with the harmonic filter and the power quality supply, for a stable grid, there is 21% reduction in the cost when I'm comparing the costs. So there is a slight 4% increase in the costs when I'm considering dynamic compensation, but this is only because of the grid when it's fluctuating such that it's from like 10% to 100%. But if we have something like a 60% stable grid, or even if we can keep the operating range between 75% to 100%, we can go with static filters, we can go even with switchable filters. So what we do is, when the operating scenarios or when the operating range is really low, we turn off some filters. So it all depends on a really strong grid. And apart from, let's say, keeping aside the IGBT, keeping aside the thyristor topic, so if I'm talking about just the grid feeding the plant, I do need a grid short circuit scenario of 2 or 3. If not, your plant is going to have operation problems and stability issues. It doesn't matter if you're an IGBT or a thyristor. So, and when we're going large scale, so I have to deal with 96 switch gears for a 1 gigawatt plant, and then here I have to only deal with 24 switch gears. So these advantages on all the other components, we believe that it compensates for this slight increase for the cost in the dynamic compensation or the dynamic filters. So again, talking about the challenges and the advantages we have. So comparing the 960 megawatt plant. So yes, the advantages with the 5 megawatt electrolyzer size is that, let's say we lose one module, we lose one electrolyzer or rectifier transformer. So we only lose 5 megawatts, and it doesn't have such a big impact on the entire system. And then there is reduced power quality requirements when going with IGBT. But it comes with a set of challenges. So I have to deal with a large number of switchgear, I have to deal with a large number of transformers. There's going to be project execution challenges, and coordinating the shipping, coordinating the logistics of a large number of units compared to smaller number of bigger units. So that's the advantage I would like to point out here. And cost of civil, erection, and installation. So this is something I've been hearing the EPC companies also say. So they like things compact. So when the area is less, the execution becomes easier, the materials, the labor, which is again an expensive matter. So all of that, we have advantages, and also it's going to take longer time to install multiple smaller units than installing one big unit. And then after that, it's the after sales services, you have the maintenance of the on-site spares. And another disadvantage I would say is that the IGBT circuits tend to be more complex, they tend to be sensitive to temperature, and they require dust-free environment. On the other side, for the 20 megawatt electrolyzer or anything greater than that, we have to go with the thyristor technology. And here we saw there's a reduction in the number of power supply units. Thyristors, we've been making thyristor rectifier for 100 years now. It's a very stable, robust technology. It's used in harsh environments, aluminum plants, chemical plants. Aluminum plants run 24/7. They cannot go off even for more than 2 hours. And thyristors are there, and aluminum plants are 1.5 gigawatt size. So I can go back to the picture on the first slide. So that's an entire aluminum plant within a small space. So, and then another advantage is the reduction in the balance of plant equipment when we are going higher on the electrolyzers. So The challenges, I would say, is, let's say, again, if I'm losing one module, which means I'm losing, say, 20 megawatt or 40 megawatt. So we have to see how to manage that, especially in weak and island grids. On a strong grid, it doesn't matter, because a small, it's going to be like a 1% or 2% impact on the grid, which doesn't matter at all. But in a weak grid, in an island grid, it has to be brought up in the initial stages so that the system engineers and everybody can work it out, and yeah, they turn off maybe the generation when the supply, when the demand is gone down. And there is definitely the need for power quality equipment, but that, again, I would like to stress, it's only on fluctuating or the weak grids. So coming to the electrification overall solution which ABB can offer, so there's right from the HV grid. So we do the HV grid compliance, HV to MV step down, HV switch gear, and then the distribution. And then from at the MV level, we will do the active or the passive power quality depending on the requirements and the grid compliance. And then coming to our core product, which is the rectifier and the rectifier transformer. So ABB has capabilities to go from 5 megawatt to 150 megawatt range, 175 megawatt. We've been doing it for many decades now. Yeah, we like big. So, and then after the rectifier, we also are competent in the DC distribution. We can support with the power backup and polarization. So we see that the electrolyzers, even when they're off, they need to be maintain some polarity. So these are very small rectifiers, but we can support there as well. And again, to reiterate, so with a 5 megawatt electrolyzers, the number of units we need, for 12 units, we have only 60 megawatt. But again, with the same number of units, I can go up to 480 megawatts if I'm feeding a slightly larger electrolyzer. And here we see 100 megawatt. You might say that it's really big, but ABB has invested in hydrogen optimized. It's a company based out in Canada, and they have a patented rugged cell technology. So they have electrolyzers which go from 50 megawatt to 100 megawatt range. So so we believe when we are going large scale, and if we really want hydrogen to grow big, it has to be in the gigawatt and the 800, 900 megawatt scale to even matter or do anything. So and then we also have offerings in the digital and the automation space, distributed control systems. So these are the DC power supply options available in the market and what ABB has. So we have DC drives which are, let's say, IGBT, the thyristor technology, we have the chopper technology, and they go up to 1000 volts in 10 kiloamps. So yeah, I'm pitching big today, but if you're a 10 megawatt plant, sorry, a 100 megawatt plant, we do still have products to cater to that range. And then we have the low current or the medium current rectifiers, which are 800 to 1000 volts, and in 6 pulse we can do 18 kiloamps and then go up to 40 kiloamps. Typically the medium current rectifier we can do for a 40 megawatt electrolyzer, and then a high current rectifier we can use it for anything in the 50 megawatt or greater electrolyzer size. So yeah, that was our products, and so we have a booth here, B36, so please do come and visit us. But one thing I would like to say and urge is we have to talk about the grid. It's about what is powering the electrolyzer, how we are powering the electrolyzer. Yeah, we can use 100% renewable grid. Is it stable? Are you going to have plant operation issues? Are you going to have stability issues? That's the question we still have to ask, and yeah, the sooner we ask, yeah, the better for us. So thank you.